Look at your watch, or the clock on your screen. Notice the steady, quiet passage of a single second. Tick. It's the rhythm of a normal day, the pulse of our shared reality. Now hold that thought and let's travel. Imagine a friend, floating in the dark near the heart of our galaxy. They are drifting, slowly at first, towards Sagittarius A star, the supermassive black hole that silently anchors the Milky Way. On your wrist, the seconds pass, as they always do. But for your friend, time itself is growing heavy. From your ship, watching through a powerful telescope, you see their world begin to warp. The beacon on their suit, which pings once every 1 of your seconds, begins to lag. A ping arrives every 2 seconds, then every 10, then a minute apart. The light from their suit begins to pay a tax to gravity, its energy draining away. The brilliant white of their headlamp blushes to orange, then a deep, dying ember red. The image on your screen begins to feel like a photograph the universe refuses to finish developing, a moment stretched toward an eternity. This place they are approaching, this threshold, is the event horizon. It isn't a surface you could touch. It's a boundary in the geometry of space-time itself, a place where gravity becomes so overwhelming that the future direction for all things points only one way: inward. The physicist John Wheeler helped give it its modern, haunting name: a black hole. Once you cross this one-way shore, no message, no light, no echo of your existence can ever return to the universe you left behind. The scale of this boundary follows a simple cosmic rule. For every mass of our sun that a black hole contains, its horizon extends by about 3 kilometers. Sagittarius A star, weighing in at about 4.3 million suns, has a horizon that spans more than 12 million kilometers. It's not a point in the dark. It is a vast, invisible sphere, a region of space larger than the orbit of Mercury. Why does your friend seem to freeze? It's because every signal they send back to you has to climb out of an impossibly deep gravitational well. That climb costs energy. For light, that cost is paid as a shift toward the red end of the spectrum, a gravitational redshift. And for time, the cost is a stretching of the intervals between each tick of their clock, a gravitational time dilation. Let's imagine them hovering, fighting their engines to stay just outside the edge. At just 1% of the horizon's own radius away, you would see their clock ticking 10 times slower than yours. Move them closer, to just 0.1% away, and their clock would appear 32 times slower. As they approach that final, infinitesimal gap, their time, from your perspective, crawls toward a complete stop. Their light pays the same toll. It shifts from red, past what our eyes can see, into the long, slow waves of infrared and radio. Eventually, the signal is stretched into a whisper so faint and a wavelength so long that it simply dissolves into the background noise of the cosmos. But you don't just see them fade. Something truly strange happens just outside the horizon. At a distance of 1.5 times the horizon's radius, there is a place called the photon sphere. Here, gravity is so perfectly balanced that a beam of light can be bent into a circle, orbiting the black hole. It's an unstable orbit, a razor's edge in space-time. If a photon strays outward, it escapes. If it strays inward, it's captured. As your friend falls past this region, their light scatters in all directions. Some of it gets trapped, looping around the black hole once, twice, 100 times before being thrown in your direction. The result? You see not one image of your friend, but a series of ghostly echoes, each one more delayed, more reddened, and more distorted than the last. These infinite echoes stack up into a thin, brilliant ring of light, hugging the edge of the blackness. For a fleeting moment, if you could look closely enough, you might even see the back of your friend's head, as light from their back loops all the way around to the front. It's the last spectacular mirage before the fall. This isn't just a thought experiment. We have seen the evidence for these one-way boundaries written across the sky. In 2019, and again in 2022, The Event Horizon Telescope delivered images of the supermassive black holes in the galaxy M87 and our own Sagittarius A star. We saw exactly what theory predicted, a dark central shadow cast by the event horizon, outlined by a bright ring of light. Seeing it required a telescope the size of Earth to resolve an object with the apparent size of a donut on the surface of the moon. We've also watched a star named S2 dance near Sagittarius A star for decades. As it swooped by in 2018, traveling at over 7,000 kilometers a second, astronomers watched its light shift to red. Its cosmic clock ticked slower, confirming the very same effects we imagine for our falling friend. And we have heard horizons form. When observatories detect two black holes merging, the final signal is a ringdown, the sound of the new horizon settling. It rings like a bell struck once, its vibrations fading in milliseconds, leaving behind a profound silence that only a true point of no return can create. But there's another boundary, further out, that shapes what we see. Long before matter reaches the horizon, it must cross the innermost stable circular orbit, or ISCO. For a non-spinning black hole, this lies at 3 times the horizon radius. Outside this line, matter can orbit happily for millions of years in a glowing accretion disk. But inside the ISCO, a stable orbit is impossible. Here, space-time is flowing inward faster than any object could orbit. It is a cosmic waterfall. Anything that crosses this line is destined to plunge toward the horizon in less than a single orbit. This is why the brilliant disks we see in artists' impressions have a dark inner edge. Most of the light comes from the turbulent, stable region. The plunging region is a swift, dim rush into darkness. The black hole's spin can change this boundary, pulling the waterfall's edge closer for matter that orbits in the same direction, allowing it to get a final, closer look before diving in. So, here is the answer to our question. Do you watch your friend fall in, or do you see them frozen for eternity? The truth is, neither. You never see them cross. Their final signal, by your clock, never arrives. But you also don't watch them forever. The universe is not a perfect, empty vacuum. There is a faint glow of ancient light from the Big Bang. There is starlight from a billion other sources. There is the inherent noise in your own detector. As your friend's image gets infinitely redder and dimmer, and the time between their signal's photons gets infinitely longer, their ghost eventually sinks below this floor of cosmic static. After a few hours, or days, or years, depending on the black hole, the last detectable photon from them will have arrived. Their fading frame becomes indistinguishable from the background hiss of the sky. The show is over. They have vanished from your universe, even though, by your clock, they never technically arrived at the end. This reveals the deepest truth of a black hole. It supports 2 entirely different, equally valid stories. In your story, The Outside Observer, the crossing is an event that is postponed to the end of time. But in your friend's story, their own watch ticks normally. They feel no jolt, see no wall. For a supermassive black hole like Sagittarius A star, the crossing itself is utterly uneventful. The tidal forces at this vast horizon are so gentle, they wouldn't even feel a stretch. They would simply float across the invisible line in a finite number of seconds, their fate sealed. The experience would only be violent near a small, stellar mass black hole, where tidal forces are extreme enough at the horizon to pull an astronaut apart in a process grimly known as spaghettification. So we have 2 truths, an eternal fall for the outsider and a swift, quiet passage for the insider. General relativity insists that both are correct within their own frame of reference. The universe doesn't have to tell one single story. And this strange warping of reality isn't confined to the edges of black holes. You are experiencing a tiny echo of it right now. The very same physics that would steal the final image of a falling astronaut is at work above our heads. The clocks on GPS satellites orbiting in a slightly weaker gravitational field and moving at high speed, tick faster than our clocks on the ground. If engineers didn't constantly correct their timing by about 38 microseconds every day, the entire system would fail. Your phone's map guides you to the right street because we account for the fact that time flows at different rates in different places. We live inside Einstein's universe. So the next time you look at your watch, remember, in a cosmos with shores you can approach but never report back from, every second that ticks by for you is your own. It is locally absolute and cosmically, beautifully strange. Our channel is a quiet place to contemplate these edges of understanding. If you find a sense of wonder in these slow journeys to the most extreme places in the universe, consider subscribing to join us again. A simple like on this video helps share that feeling with others who might be looking for it. There is always another cosmic question waiting. We'll see you out there.